So let's see.
Hello, Abhay sir. It
Yes.
looks like your network is not good.
I'm not sure why is that, because so usually connectivity is using Wi-Fi. Is it better now? Sorry. Is it better now? Okay, so give me switch to some alternative.
Sir, it's showing low bandwidth on your side, especially on SRM. I'm seeing it as low bandwidth issue.
Anyway, so is it better now?
Yes, sir.
Right. Yeah. Good morning, and I would like to thank organizers, especially Professor Vimla Juliet, for inviting me to share my thought to people. So to start with, I am a team member and associate professor in Institute of Science and Technology, and I'm 3.5 years. So if you have any, or if you would like to conduct any particular research, please feel free to call me on this my email ID, and you can see my research activities on the website. Some of the new results from my group, as well as from general and this is related to new generation of nanoscale devices for electronics. To start with, I would like to acknowledge the financial support from SCRB and SRM, and the work which I will be sharing. It was done with my colleagues from Cambridge University, then AMO from Germany.
Sir,
1 second.
can you hear my voice, sir?
Hello, madam.
Sir, can you hear my voice?
Yes.
Can
yes.
you hear? I think you can sign out and then join again, sir. But only because now network issues are rising. Please, we will wait for another few minutes.
I see.
We will wait. You sign up, join.
Okay. Fine. Hello, can you hear me now, madam?
Yes, sir, we can hear you, sir.
Yes, okay. So maybe I will not start a video so that the bandwidth can be better. Yes, madam.
You can start, sir. Participants, if you don't hear his voice, please tell us, okay?
Yes, please.
So that
Yeah.
he can redo the his presentation as well. We will not miss any of the contents also.
Right.
Notification if you don't hear.
Yeah. So the first question arises is that we're going to look into the RF part of electromagnetic spectrum and use it for the electronic applications. So the first obvious answer is in the 21st century, there has been an explosion. So these days, every day, we are using this technology very efficiently. And some of the examples, what we know, what I write technical words for it. So this is like a 3 to generation of cellular phones with extended functionality. So for example, internet and some other facilities in that. It's satellite communication services such as direct broadband satellite, means dish TVs which are coming directly to our home. Then wireless networks, especially Bluetooth. Or these days even smartphone comes with a connectivity own apps where you can share the data in a closed loop. So all of this needs RF electronic devices, and physics behind it is that when the waves of electromagnetic spectrum come on the surface of any material, then those waves penetrate inside it or they are emitted from the surface or not is called as a skin depth. So as you can see it in this schematic with the comparison between DC and AC. So when you pass a DC current, visible, madam?
It is visible, sir. It is visible.
Okay, because I saw some message showing that slides are not visible.
Why RF electronics? It is visible.
Okay.
I think
I will go ahead.
Rajendra, sir, I think network issues on your side. Please check your net. Otherwise, sign out and then sign in. We are able to see.
Right.
We are able to see.
Okay, madam. So when we flow DC current through a conductor, then what you are seeing is a cross section. The current is flowed from the surface as well as throughout the bulk. But when you apply now AC current, then you will see some portion of the current is not getting filled with the electron flow. And if you increase more and more frequency, then you will see the conductivity is only getting restricted only to the surface. And that's what is called as a skin effect. If you say some of the commonly used materials, then is that
Hello.
Not audible.
Sir, your voice is cut, sir. I can hear your voice. Sir, we couldn't hear your voice.
So, Abhay sir, your voice is not heard.
So is it audible now?
Yeah.
I'm speaking. Is it audible now?
Now it's audible. Yes, sir. Yes, now it's audible.
Hello.
Now it is audible, sir.
Yes, yes.
Okay. Now it is audible.
Okay, okay. Right. So we'll continue now.
Yes, sir. Yes, sir.
Right. Yes. So whatever the questions you have, you can post right now in chat. So that we will take the questions at the end. If any something very important is there, then you can turn on your microphone and ask. So that's why we differentiate between two types of resistances. One is called a DC resistance and second one is AC resistance. So usually, depending on, you can see it here in the frequency range, your DC resistance usually are smaller and AC resistance is larger. So the backbone of RF systems or the RF based devices, what we see is this effect only. In this 5 days program, many different devices will be discussed, but I will be focusing only on two devices. One is called a 2-terminal and 3-terminal devices. One of it is a diode and second one is transistor. So specifically RF diodes and RF transistors. So other devices like MEMS, names, you will be hearing from some other talks also. So when we are talking about these RF devices, first question which we should ask is that how we can define their figure of merits. The first one is called as cutoff frequency and it is denoted by Ft. And the second one is the maximum frequency of oscillation. It is indicated by Fmax. So then depending on the applications and the way devices are fabricated, the values of Ft and Fmax can be same or one of it is higher and other one is low. The next one is minimum noise frequency and it is indicated by NF minimum. This is the noise present in your signal. Okay, and of course it has to be minimal. The third parameter is the output power of the RF and usually the more is the power, better is the your performance. Apart from this, there are other parameters are there which we will discuss with due time. So I will not directly jump into the electronics part of it, but I will bring this perspective from materials physics point of view. So when we talk about materials, all the materials are like gas, liquids, solids, and they form various interfaces with each other. So as per my understanding, so some of the interfaces are easier to control and some of them are not. So basically by using various these interfaces, we develop various applications like gas-based applications, liquids, and their interfaces like gas sensors, where the gas interact with a solid and there is a formation of particular interface, and we call that as a barrier height, and the change in the barrier height is considered as a sensor signal. But here today I will talk only about solid-solid interfaces. So when we talk about solids, we know we have metal, semiconductor, an insulator, and the next one is a superconductor. So we can form interfaces between each of these materials and come up with various new types of electronic devices. Even the interface superconductors and metal insulator and semiconductors are still very new, because controlling the superconductors or getting the superconductors and then interfacing them is a big challenge. So defining the surfaces and interfaces is one of the key point. So Wolfgang Pauli, who is a very well-known quantum physicist, when he learned about this new properties of the materials in early 1930s, then he said that God made the bulk, but surfaces were invented by devil. So he immediately or spontaneously said like that because he knew what the surfaces means. So if I have to tell you an example, then the very famous example of a metal is a copper, which we see all around. So when you flow an electron through it, then we get very good current. But when we try to look at its surface, any of the face if you take, then its a surface looks like something like this. And this is what we call it a nanoworld. So if you have to flow a single electron on its surface, then what electron will experience is shown here in this animation. So all these small dots what you are seeing here, these are the small defects, and these lines or the wrinkles which you are seeing, these are purely quantum mechanical oscillations at the surface. So these are the combinations of phonons, then electrons, and some other kind of vibrations. So as you can see, electron gets scattered from each of them. Then if you are seeing this, what is this top to this surface, this height is hardly 2 nanometers. Okay, and there are some terraces through which the electron has to travel as it is shown here. So then you can imagine now how it is difficult for an electron, a tiny particle like an electron, to travel through a surface compared to a bulk. So to give you more insights, so there is a very good review paper here in Journal of Physics. You can see this. So this picture I have taken it from that. So what you are seeing is that what the electron can see at each and every of steps here. So these are called as a quantum mechanical confinements, then adsorption, desorption, particular form of ordering, And when a spin of electron becomes important, and contacting to these kind of materials with particular material, it itself is a challenge. So understanding the surfaces and its interfaces has revolutionized an evolution of has taken place in electronic industry. So the next parameter which we have to consider is its electronic band structure of the material. So I will not go into the more details of this because it is very much textbook kind of stuff. So just note that when we talk about energy band diagram for N-type and P-type material, then we consider bending downwards, upwards, or any of it in more towards deep inside the bands. And when we apply electric field to it, then there is a band motion, and this is what controls the charge transport in a device. Now, depending on which material we are using, whether it is a metal or a semiconductor, and whether it is a p-type or n-type semiconductor, or whether there is a insulator in between the two, there are various types of junctions. So these are ohmic and Schottky junctions. Again, I will also not go into the more details of these definitions, but when you try to make more various types of junctions, these are called as type 1, type 2, type 3, and these are basically used for solar cell applications. So, but right now what we are going to focus on is only on these two types of junctions. One is ohmic and second one is a Schottky. So in this presentation, I will take two examples. One is Schottky diodes, and second one is in terms of I will not talk about the all general RF transistors, but only new generations of graphene transistors. So to start with Schottky junction, this is a brief overview of a Schottky junction, which is a junction between a metal and a semiconductor. But we also know another type of junction. It is called as a PN junction, and it is made when a junction is fabricated between a semiconductor and a semiconductor with two types of conductivities, p-type and n-type. So these are the energy band diagrams for it. So if we compare now the IV characteristics of it, then this blue line is for a Schottky junction and the red one is for a PN junction. So immediately what you can notice is that within a voltage region, when there is no current flowing in a PN junction diode, you can see there is an immediate current is flowing in a forward bias for a Schottky diode. And this is what makes a Schottky diode a special device for high frequency electronic devices. Why is that? Is because when we talk about RF devices, we here consider the speed of the device whether it is switching on and off. So in this diagram, what you are seeing is the current with a high value, and this is the current in a forward direction, and it is in a reverse direction. So this is large current and this is low current, and it is plotted as a function of time. So what you can see is that going from high current to low current and going back to it, it has a particular time which is represented here by TRR. So if you compare the time between Schottky diode and PN junction diode, then you can see that Schottky diodes are already 1000 times faster than PN junction diode. And that is what is required for RF applications. So I'm going to share some of my new results, which we published a couple of months ago in Nature Electronics. And the title of the paper is 100 gigahertz zinc oxide Schottky diodes, which were processed by solution on a wafer scale. So some of my colleagues are from Imperial College London, then KAUST in Saudi Arabia, and there are a couple of companies from Finland and England. So why this study was important is that actually we took almost 4 years to come up to start the work and completely finish it by publishing it. So and luckily at the end of January 2020, this journal Nature Electronics declared 5G is the technology of the year. So they shared a lot of new articles and emphasized how this technology is important. So in 5G, when we talk about the communication networks, and one of it is called as a near field communication. So right now it works at a frequency of 13.56 megahertz or a Bluetooth frequency of 2.5 gigahertz. So when we look at now these new 5th or 6th generation mobile phones, they are now considering a 5 gigahertz Bluetooth frequency. One other type of near field communication, what we know is RFID tags. So we use them on our daily basis. So, but it is important to maintain the security of these tags. And that's why all over the world, there is a important requirement to switch a frequency from 13.56 megahertz to a little bit more higher frequency in the range of 900 megahertz. So this is actually a circuit diagram which is built between a reader and RFID tag. So this is basically an inductor. There is a power source, DC source from one side, and then it is coupled to a circuit inside the RF tag, and its circuit consists of one diode and some resistors and capacitors. So combinedly, a rectifier, a diode called as a rectifier, and there is an antenna here, is combinedly called as a rectenna. Okay. So when we consider a silicon as a very famous electronic material, then it is very difficult to make these devices working for a silicon above 3 gigahertz. That's why in last 20 years, many new materials have been proposed for it as a competitors. So this is one of the graph from our paper, which shows the requirement of the frequencies for various 4th, 5th, and 6th generation of communication, and the technology developed over a year. So some of the competitors are carbon nanotubes. So back in 2008 and 10, these were shown to be very promising materials where they were operated or showing the cutoff frequencies in the range of 10 raised to 11 hertz. But controlling these devices and getting the high reproducibility from them has been challenging or not up to the mark. And that's why zinc oxide based materials like indium gallium zinc oxide, or its short is IGZO, has come up with very new improved performance, and that's why this is being preferred right now in the industry, and it shows a good cutoff frequency up to 10 gigahertz. So the invent of new 2D materials, or 2D specifically chalcogenide materials, these are MOS2 and WSA2. They have also in last 1 or 2 years had showed good cutoff frequency in the range of 10 gigahertz. But what we want is a cost of the materials needs to be considered. So to the best of our knowledge, in last 4 or 5 years, the maximum working frequency or cutoff frequency which is reported for zinc oxide, which is a very well known material and it can be synthesized by various techniques and it is easily synthesizable. So the cutoff frequency well known is like in the range of half a gigahertz. Okay. So that's why we decided to make use of this material and work on the various designs of the material, of the devices, so that we can make the cutoff frequency in the higher order. So yesterday you heard about the various lithographic techniques from Dr. Malar. So I will not repeat the same things. So you came to know about various lithography techniques like photolithography, lithography, electron beam lithography, then imprint lithography, and these days one of the lithography is called as ICE lithography. So all of these lithographies are used to make the device dimensions smaller and smaller. So, but today I am going to share with you another type of lithography which my colleagues at Imperial College London have invented, and it is called as molecular adhesion lithography. So it is a extension of this imprint lithography. So this is a combination of imprint and photolithography. So on this slide, I will share the steps involved in this molecular adhesion lithography. So to start with, you take a substrate, insulating substrate, then pattern one of the metal. It is written here as a metal one, and you will see. So this is done by standard photolithography, UV photolithography, and then dip this whole substrate in a particular kind of self-assembled organic monolayer solution. So take a beaker of this filled with these SAM molecules in a beaker with one particular solvent, and dip this whole substrate inside it and leave it there for a couple of hours, and then only the metal one surface, look at here, only the surface of metal one is occupied with this SAM layer. Please note here that not just only on the top surface, but the vertical edges of the metal is also occupied by the 90-degree orientation of these SAM molecules. So what you can notice is that the empty region between the two metals, which is a substrate, let's call it as a standard silicon dioxide substrate, then there is no SAM molecule present here. And that's why in the next step, you can deposit a second metal which do not get attached or has an interaction with this molecule globally everywhere on the substrate. And then in the next step, so let me show you a video. Then on the top of this second metal, you apply a glue as it is shown here in this video. So this is a regular glue, not a regular glue, but a special kind of a glue, which has the special property of getting dried immediately. And then you just peel off that glue and it will take away the metal too with it. But only the regions which are coated on the top of the SAM molecule are only getting lifted off. And that's why you can hear in this video, the metal one, it stays there and the metal 2 is separated from the metal 1 by a distance which is almost equal to the length of a molecule. And at the last step, now you expose this whole substrate to UV light with ozone, and it will burn away all this organic SAM molecule. And you will end up with a substrate with one separated by a distance which is equal to a length of a molecule, and then metal 2. So depending on the length of a molecule which you have used, you can end up with a gap between the two metals starting from 5 nanometers, and the maximum what we could achieve is a 25 nanometer. So the size what you are hearing, the 5 nanometer to 25 nanometer, they are very challenging to obtain from photolithography. Of course, it's very difficult. Then electron beam lithography is also one of the options, but access to it is not that easy. But with this combination of imprint lithography and photolithography, you can obtain a small nano gap electrodes of the order of 10 nanometer. So there are various control parameters are there to obtain these nano gaps and which decides the yield. So when we talk about making a diode, what we need are the two metals, metal 1 and metal 2, and they are separated by a semiconductor. Why I'm saying all the time metal 1 and metal 2 is because we have to use a metals, two metals with different work function compared to work function of a semiconductor. Then we can actually fabricate devices in two different geometries. One of it is called as the sandwich geometry, or what you can see is a parallel plate capacitor geometry. And the second one is a planar structure, where a semiconductor is below the two metals or above two metals. Okay. So, but the advantage and disadvantage of these two structures is that this one is little bit easier to fabricate, but because of the larger dimensions of it, it has a very large capacitance. And because of it, these devices cannot be operated at high frequency. With this planar structure, as you have seen, they are little bit difficult and tricky to fabricate, but they have very small capacitance. And that's why you can operate this or expect these devices to show a cutoff frequency above 5 gigahertz. Apart from that, the one more advantage of this planar structures is that you can have or you can expect reduced parasitic capacitances and higher current densities. I will share some of the data in few minutes.
आज की मैंने खबर याद दिलाती हूँ तो ये चीज डाल देना मुझे ठीक है खबर याद दिलाती थी
Hello,
बजट डाला नहीं डाला तो
is there a comment?
ठीक है मीटिंग बोलो ना फिर बाद में बात करें सर मीटिंग मेरा बच्चे
Okay, so another advantage of this molecular adhesion lithography is that you will get metal gap electrodes with two metals or metals with two different work functions, which is very difficult to get it from other lithographic techniques like photolithography and electron beam lithography in single step. You have to do the same processing twice. So it will increase the fabrication time. So now once you have this set of electrodes on a substrate, then you can deposit your semiconductor on the top of it by all the deposition techniques. So the technique which we selected here is a spin coating technique. So we took a syringe with filled with this zinc oxide nanoparticles in it and spin coat it so that the solvent is evaporated and we end up with a film of zinc oxide. So here we use the two types of zinc oxides. One is pure zinc oxide and second one is aluminum doped zinc oxide. So this aluminum doping, it has one small advantage. I will share it to you in next couple of slides. So you can see it here. This is a cross-sectional TM image where you can see there is a gold electrode on the left side and the second one is aluminum. So these two metals have a 5.3 electron volt and 4.3 electron volt, and you can see this aluminum is doped zinc oxide. It is short is AZO. You can see that it fills in between the two. So this is a small range between the two of the dimensions of around 15 nanometer, and now you have a metal, semiconductor, and metal junction. So we have fabricated these devices over 2-inch and 4-inch wafer. You can see this is a photograph of hundreds of devices on this chip. So to now share you something about the design of the device. What you are seeing it here is a cross section. Okay, but if you see a top view of it, then the devices are actually in a circular geometry. So the outer white colored ring is made up of aluminum metal, and then the inner circular ring of yellow color is a gold, and there is the nano gap is all around this violet colored ring what you are seeing. So if you zoom in, then you can see the nano gap is there in between and it is filled with a semiconductor. So this kind of a geometry we simulated and found that it helps to operate the devices at higher frequency with less parasitic capacity. Now for beginners, so one of the important questions is that what we can do, what kind of measurements we can do for these kind of devices and what kind of tools are required. So first is in terms of the instrumentation. So what we need is a DC source, then current meters, then frequency generators, some voltmeters, and some one particular kind of a circuit, which I will show you shortly. This is one kind of electrical probe station is required depending on your frequency requirements. So now in terms of the performance of the devices, of course, we have to look at the two parameters. One from the DC parameters. So these are the current on-off ratio, then ideality factor, then the non-linearity of the IV characteristics, and the responsivity. So I will show all of these parameters for our device. So when you going to look at the IV characteristics, what you will be seeing, the currents, these I1 are plotted either in a linear scale, then you will see the IV like this in a black line, and when it is plotted in a log scale, then you can see it will have the shape of what is the shape of this white line. When it comes to now AC measurements, we have to consider impedance. So the impedance is a complex parameter where it consists of a real part, is the DC part, and the AC imaginary part. So it is written as Z is equal to X plus IY. So we now have two values of resistance, and we can plot them on a same graph, which is done here in this graph, which is a y-axis is impedance and x-axis is as a function of frequency. Then you will see the real part is almost flat or non-varying, while the imaginary part varies or decreases almost linearly. And that's why when a point comes when the values of the both becomes similar, then that is called as a cutoff frequency. And because of its the way the measurements are done. So there are two types of cutoff frequency. One is called as intrinsic cutoff frequency, and second one is called as extrinsic cutoff frequency. So what is intrinsic? So it means that only a diode, an independent diode, has been measured here, and it shows the intrinsic original performance of a diode. And extrinsic frequency is the one in which if you connect the diode in a circuit, then what will be the total cutoff frequency of that circuit. So here we have fabricated a rectifier circuit and measured its DC output voltage. So what you are seeing it here. So this is a DC out. When you give a AC in, we are seeing a DC out. So that is the output voltage which is plotted here on y-axis as a function of frequency. And going with the standard the rules of cutoff frequency, when this DC voltage, so the maximum DC voltage, when it drops by a value of 3 dB, then that value of frequency is considered as a cutoff frequency. So for the beginners, again, I would like to share one more information, is that these diodes are measured for RF performance using a parameter called as S parameters. So those who already are aware of it, they know the importance of these S parameters. These are basically the ratio of output voltage to the input voltage. So if you are using this kind of a device, it is called a device under test, DUT, and you have input port and output port. So depending on which from where you are collecting your data, within the input side or output side or a transmission side, then you will have 4 S parameters, and these are labeled here. These are called as S11, S12, S21, and S22. Okay. So I have simulated these devices before its fabrication and measurements and obtained the S parameters. So I have not shown here all the parameters because I have measured on going to focus only on S11, which is a reflection parameter, and second one is S21, which is a transmission parameter. So what you can look at here is that S11 is almost stable and flat. Please ignore various colors because they are these are at different voltages. Only look at the smallest voltage or close to 0 volt is the black line. Then you can see it is a completely flat line up to terahertz frequency. Okay. And the second, if you look at the S21, then you can see the variation is appropriately linear up to that same frequency range. From these parameters, S parameters, you can obtain a capacitance of the device. And it has to be very, very low. If you want larger cutoff frequencies, then this capacitance has to be very low. So the low means, to quantify it, you can see that the value of the capacitance is almost 0.34 picofarad. Okay, so if you look at the capacitance of commercially available diodes, then it is in the range of 3 to 10 picofarad. So this capacitance is almost 10 times smaller than that. And that, as you can see it here as the S parameter, this capacitance is almost flat or unchanging up to terahertz frequency. This is the simulated data for intrinsic cutoff frequency, as I mentioned in the previous slide. So this is the real part, the black line is the real part of it, and red the imaginary part. And these two lines touch or cross each other at a frequency of 0.8 terahertz or 800 gigahertz. Okay, so this gave us a confidence or the direction that whatever we thought about the its design and the materials use is correct, and finally we will be able to have a devices above 100 gigahertz. Okay, so now I will show you the experimental data, and to start with, it is important to know what is DC performance. So this is the IV characteristics. Uh, uh, Y-axis is the current and X-axis is the voltage, and it is shown only in forward bias direction. And this is the schematic of the. This is a real-time picture of a diode. As you can see, one of the contact is taken from gold, and second one is from aluminum. And these are the various colors are for the various dimensions or the width of the inner ring, this gold ring. The smallest is 250 micrometer and the largest one is 5000 micrometer. So if you plot this graph in a log scale, then you can see both reverse and forward voltage characteristics. So in the reverse voltage, the current is very low, which is 0.1 nanoamperes, and when it is in forward bias, it is 0.1 milliampere. Okay, and this is the comparison between zinc oxide and aluminum doped zinc oxide. So what you can notice here is that after aluminum doping, there is a small reduction in the current. Okay, so I will show it in the next slide how this reduction in the current is advantageous from RF performance point of view. The next parameter which is plotted here is called as the rectification ratio, and this rectification ratio is the one which decides up to how much frequency you will be able to get good DC voltage, and this has to be larger and larger as much as possible. So this is typically is in the range of above 10⁵. Okay, so this is the ratio of on current divided by off current. Hello, yes, is there any comment?
Hello, sir.
Yes.
Sir, I have a small doubt.
Yes.
Sir, whether we need to fix the materials or we need to fix the gap. So what is the relationship between the gap and the frequency?
So can you come again? What is the
relationship between the nano gap and the frequency, sir, and the operating frequency?
Yes. So it is not so what you see it here in this schematic as I shown you previously in this one, the separation between the gap decides the total capacitance of your device. If you make this gap smaller, then you will have a little bit larger capacitance. But apart from that, what you have to see the total capacitance also of the which is coming from the pad. Okay, so that is called as a parasitic capacitance. So capacitance between the two electrodes in the junction is called as a junction capacitance, and the total capacitance comes from the pad area also. Okay, and that's why you have to worry about both the capacitance values.
Okay, sir.
And the capacitance which I showed it here is a junction capacitance.
Okay. So regarding material selection for semiconductor.
Yes.
So which property we look into, like say you have chosen certain row, then a combination of aluminum and certain row. So
right.
How to choose the materials? So which property of the material will decide the frequency?
Yes. So actually, this is you can understand from this graph itself. This slide. So one of the parameters is actually you have to have very high on current. Means you should have a semiconductor with appropriate doping in it. Then the second one is that if turn on voltage means where the current start increasing, it should have very small threshold voltage. Okay. And the third one is that is the mobility of the material or the charge carrier in the mobility. So it should be sufficiently good. It is of the order of above 10 centimeters square per volt second, which allows operation at higher frequency. Okay.
And one more thing regarding simulation tool, you have mentioned you have done the simulation part also.
Right.
So which software?
Yes, so this simulation was done TCAD simulations using software Silvaco.
Okay, okay, TCAD only. Okay.
Yeah, TCAD Silvaco.
Okay. Thank you, sir.
So the next parameter which you have to think about is responsivity. What you are seeing is that it is obtained from this equation. It is actually the derivative of this current and voltages. And you can see the maximum responsivity is there, and its unit is ampere per watt, and it is maximum close to 0 volt. And you see we have obtained a value of 11 amp per watt. So for a silicon, which if you have to compare, then it is hardly in the range of 3 to 5. So the value which we have obtained is almost 2 times larger than that. From industrial point of view, what they think worry about is the non-linearity. Means how good is your rectification ratio. And again, surprisingly, it has to be again more than 3. So the value of non-linearity has to be above 3. And as you can see it here in both this ZNO and AZO diodes, throughout the voltage range of the forward voltage, the value of it is above 4. So these are actually the parameters, the DC parameters, which gave us a confidence that the devices which we have fabricated of very good quality. To give a comparison with the literature, so this graph shows the progress of the current responsivity, which I just told you in the last slide, with over the years of various types of diodes. So you only look at this theoretical limit for Schottky diodes, or which comes from the thermal vibrations, and it is around 20 amp per watt. So this was achieved with various companies in last 20 years, but the material specifications is very stringent. Okay, not many materials can achieve this kind of values. And here in 2020, we achieved almost close to that theoretical limit. Right. So this is the now slide and the graphs which indicates how the devices are working from the semiconductor device point of view. As we know, zinc oxide is a very good semiconductor, but if you see its energy band diagram, then you will see this yellow color, blue colored shallow states in it. Okay, and that's why when you have these shallow states, as I told you in one of the introductory slides, when conduction takes place in these semiconductors and metals at higher frequency, the damping may occur at the surface because of these shallow states. But when it is doped with aluminum, then these shallow states are filled by aluminum, and you will end up with only deep states. And that's why the propagation of the wave and the charge carriers will be more smoothened out. Okay, so you will what we can expect is that AZO device is going to show better cutoff frequencies than the pure ZNO. So this is the last graph of the DC parameters, and it is called as chain plot. From this one, you can obtain a series resistance of the diode. And this is again one of the industrial parameter which needs to be obtained, which has a, so if you understand the series resistance concept, then this is the series resistance in series with the source and your diode. And obviously, as you can expect, this has to be as small as possible, or at least more than half. Its value should be less than half of the total resistance of the diode. Right. So when you are going to measure its AC performance, then as I told you, we have to measure its intrinsic and extrinsic performance. So to measure its extrinsic performance, you have to build a circuit like this, and these are the components or the setup which you need. You need a software which controls this function generator and DC power source. Then you need a probe station to probe your device. Then some very good quality RF probes. And specifically, there are two components. One is called as a bias T, and here the last one here is called as a load resistor or a matching circuit. Okay, impedance matching circuit. So you have to work out all of this appropriately to get better device performance. So this is a typical one of optic photograph which shows this RF probes. Then this is a chip of fabricated diodes, and this is a zoom in of one of the diode, and these are the RF probes touching the device. Here the central tip is called as a signal, and outside these two are called as a ground. So these are called as GSG probes. Now, why this setup is important is because there should not be any vibrations. Then it should have extremely low parasitics, then high signal to noise ratio, and there should be a very good LCR matching. So all these parameters you can actually subtract from the environment using a calibration of the device. And this is very important step before starting your measurements. Each and every time your setup should be calibrated. So this is a standard chip which you can buy to calibrate your device. And this is the second unit. It is called as vector network analyzer, which is required for measuring its intrinsic performance. So I will start with the extrinsic performance of the device. So this is the DC output voltage, which is plotted as a function of frequency. For a diode which has dimensions of 5 mm and 500 micrometer. Then this graph was plotted, or the data was obtained for two input powers at 0 dBm and 5 dBm. As you can see, for a 5 dBm, 0 dBm, the cutoff frequency shown here is a 3 gigahertz, and when you increase it to 5 dBm, it goes to 3.6 gigahertz. For the larger device, and when you make it a device dimension smaller, then you can see this cutoff frequency is increased from 3.6 to 5.7 gigahertz. And that's why we have plotted here in this graph output voltage, maximum output voltage obtained as a function of input power. So this is the formula you can use to obtain your cutoff frequency. So this data points is experimental data, and the line is a line fit obtained from this equation. So what you can see is that smaller the device, better its performance, and called as a scaling at higher cutoff frequency. So this slide shows intrinsic cutoff frequency or the RF performance of the diode. As you can see it here, impedance is plotted as a function of frequency, and this is a bottom is the real part, and the vertical line, which is slanted line, is coming as a imaginary part. For zinc oxide and aluminum doped zinc oxide, as I told you in previous slide, we can expect a little bit better performance from AZO, and as you can see it here, cutoff frequency for zinc oxide was 38 gigahertz, while for AZO it is 60 gigahertz. Okay, so this is a significant improvement. So from now onwards, I will show you the data only for AZO. So this is a scaling of the devices where we have shown a comparative comparison of 5 mm, 1 mm, and 500 micrometer size device. And as you can see, the cutoff frequency is increasing from 6.6 gigahertz to 60 gigahertz to 330 gigahertz. Okay, so this 330 gigahertz is the maximum cutoff frequency which is reported for any other material than 3.5 materials. And as you saw in the previous slide, so simulation has shown that this can go up to 800 gigahertz. So small optimization is required again in the devices so that we can go above 330. So as I mentioned previously also, the capacitance is important to see. So as you can see, capacitance is completely flat up to 10 gigahertz. This data is shown up to 10 gigahertz, but basically it follows the same trend as what we have seen it from the simulation. Now, if you are curious, and I will show you one example for two-dimensional material semiconductor MOS2. So this data was result was published from MIT group last year in the Nature journal, so where we have fabricated MOS2 Schottky diode with very novel heteroscopy, and their devices were operating up to 20 gigahertz. What you can see it here, they are operable up to 20 gigahertz. So that's why I said even 2D materials looks promising. A lot of work needs to be done. So this slide shows the importance and of additive lithography. As you can see it here, we can make a directly full wave rectifier on a chip, or you can even various other display materials. Displays also. Here you can see there are various colors are coming from this nano gap, because if you add very for organic materials in that, you can get very small scale displays also. You can make these flexible substrates. So now in last 10 to 15 minutes, now I will share the second part of the talk, and it is related to graphene transistors. So again, to give a small introduction, I will not go into the details from the materials perspective, because all of us now we know what the graphene is. For me, graphene is only a monolayer of carbon atoms, and the bilayer, trilayer are little bit less important for this transistor application. So here I am talking about a transistor, and it is specifically field effect transistor and not junction transistor. So when we look at the transistor, what we know, what we want is a source drain electrodes and a gate which is separated by insulate. So if you look at the scaling theory, then it predicts that you have to have very thin semiconductor and dielectric layers, so that when you reduce your scale of a device, then you can have better sustainability or better performance. And that's why atomic layer materials like graphene have become important for RF applications. So if you look at its equivalent circuit, small signal equivalent circuit, then you can see this device is made up of combinations of a couple of capacitors between source and drain, then gate and drain, and gate and source, and a couple of resistors. So what we have to look at are the parameters are intrinsic conductance, which is a ratio of drain current as a function of gate voltage. Then drain conductance, it is a ratio of drain current as a function of drain voltage. Then gate source capacitance, gate drain capacitance. And from all these parameters, you can obtain a cutoff frequency from this formula. What is important to be noticed here for RF transistors is that there is no as such of the transistor is required. So what we know for transistors are well known to be used as an on-off switch, where the off state is important with very low current. But for this RF applications, state with low current is not required. The bottom line is you have to have shorter gates, then fast moving charge carriers, low series resistance, low parasitic capacitance. Important, you have to have a saturation in the output current. Okay, so these are the parameters which need to be all watched out when you are going to fabricate your device. So let me tell you now what it means, high-speed charge carriers. So this is a graph from this paper from 2015, in which mobility of electron is plotted as a function of its charge carrier density for various materials. Okay. This dotted line represents the theoretical limit for a particular material. As you can see, very well known and high performance materials are compared here. One of it is a indium antimonide, which known to show one of the best mobilities in the range of 50,000 centimeters square per volt second at room temperature. Then there are indium arsenide, indium phosphide, gallium arsenide, and of course there is silicon also. But compared to all these materials, graphene shows a mobility which is shown here by a solid line. As you can see it here, at a carrier density of 1 into 10 raised to 12 per centimeter square, the mobility in a graphene is 100,000 centimeters square per volt second. So which is way better or higher than any other material. Okay, and that's why the graphene has been known, or it has been investigated right now for applications. So this is a state-of-the-art comparison from the literature, which shows the cutoff of frequency obtained for various materials, these materials, as a function of gate length. So these are the very standard materials. This red line, which is for indium phosphide, which shows one of the best cutoff frequencies around the 900 gigahertz. Okay, 700, 800 gigahertz. And the star values are for graphene. So within a very less than a decade of this discovery, as you can see, this star point, which shows a cutoff frequency around 450 gigahertz, graphene is able to compete with very well best materials. So in next 3 to 4 slides, I will share with you what kind of device geometries are required to get best performance from graphene transistors. So this is one of the example where the gate electrode is little bit larger its dimension is like 1 micrometer. And from this device, you can get a cutoff frequencies. So both cutoff frequencies are mentioned here. One is FT and the second one is Fmax. And you can see both values are close. So this is one of the rare examples of design where both values of this FT and Fmax are nearby. And this is one of the requirement for a device if you want to use it for a Bluetooth application. And second parameter what you have to know is the forward gain, which is the S21 parameter, which is shown here. It is the blue line, and you can see its value is about 10 dB. So this is a very large value, and it is useful for a Bluetooth application.
Lab design.
Hello, is there any comment or question?
ATAL.
Hello, participants. Thiru, please turn off your microphone. Yeah, thank you.
Loading.
Yeah. The second example here is for selecting a particular substrate. So this is an example in which a silicon carbide is used as a very good quality substrate, and where graphene is used as a channel material. And as you can see, cutoff frequency now is increased to 155 gigahertz. So what you are looking at this extension of the data, and it touches here when the gain H2 is 1. So this is cutoff frequency, and the cutoff frequency is 155 gigahertz. And the value here is actually FT and not Fmax. So when you make this kind of devices in this geometry, then the big difference between FT and Fmax. So even if we are seeing FT is above 150 gigahertz, if Fmax is actually very low in the range of 5 to 10 gigahertz. Okay. So when it comes to a scaling, this is the scaling graph. What you're seeing is cutoff frequency as a function of gate length. This is required to understand Moore's law. As you can see, as the gate length is smaller and smaller, you will be able to get higher cutoff.
Now from page number serial number volume page number
Hello, participants, please mute yourself. In this next example, you can see it here. The gate structure of gate electrode is completely flat. But you can make new type of gate where the gate looks like something like this. It looks like a T. The shape of the gate electrodes looks like a T shape. Okay. So this is done by using a fabrication technique called as a self-aligned fabrication technique, in which source drain metal electrodes are almost of the same parallel to the gate electrode. Okay. And here, gate oxide used is aluminum, an aluminum oxide. But the oxide is not deposited deliberately from other techniques, but it is naturally grown aluminum oxide.
CMOS logic. பார்த்துட்டு சரி இதை பார்த்துட்டு மெட்டீரியல் பார்த்துட்டு பண்ணோம் அப்படின்னு வச்சுட்டேன். ஓ இப்ப சத்தியமூர்த்தி போட்டு தான் நீங்க பண்ணிட்டு இருக்கீங்களா? இல்ல நான் இந்த வாரம் எதுவுமே பண்ணல.
Okay. Yeah, sorry for the disturbance. Yeah, this is next. So because of this fabrication technique, where the T gate is fabricated, these devices are now operating with even higher frequency in the range of cutoff frequency of 180 gigahertz. So this is the second last example in which this is a very special fabrication process in which a gate electrode is fabricated in the form of a nanowire and a local oxide is formed on the top of it using atomic layer deposition technique, and this gate electrode is brought in contact with the channel material at the last stage. Okay, you can see the schematic of it. And because of this spatial fabrication, the cutoff frequency obtained for these devices is 427 gigahertz. Okay, and this is the example of a star point which I showed it in the previous slide. Okay, so this is the record for right now for a graphene transistors with a cutoff frequency of 427 gig. And in the last example, where now these are all the intrinsic cutoff frequencies, but when you make a circuit out of it, means you have to make a passive circuit and you have to integrate a graphene transistor with it. Okay, so the passive circuit means, as you can see in this example, in this schematic, what is fabricated is inductor, then there are some capacitors and resistors. So this forms a LCR circuit and you have to integrate a graphene transistor within it. Okay, please note that this metal one, which is used for to make an inductor, it has a thickness of 1 micrometer. So why is that I will tell you it in the next slide. So 1 micrometer is a very, very large thickness. If you have to make the structures on the chip, then 1 micrometer is a quite large thickness. And so that's why the fabrication of this circuit from IBM, they came up with a new design in which a gate electrode is embedded inside the substrate. Okay, so when you are looking at this silicon substrate, these are the gate electrodes. These are embedded below inside the substrate. Okay, and that's why it reduces the noise and improves the signal. And that process flow technology, they called it a passive first and active last. The passive first means all these LCR components are the passive components. So you fabricate those first because they require high temperature in the range above 400 degrees centigrade. And at the end, you fabricate active component like a graphene transistor. So this is the receiver circuit, which is fabricated. So what you are looking at here, these coils are the inductors. So there are 4 inductors. Then there are a couple of capacitors, C1 and C2. And these are the 3 transistors, T1, T2, and T3. And when you try now to probe it, then this is the RF probe. And this is second RF probe, where you supply RF signal and look at its output in the form of a intermediate frequency output, and these are the regular DC probes which are used to bias a transistor. Okay. What you can get is the frequency of a local oscillator. So this is actually called as a oscillator circuit, and it has a cutoff frequency of 4.8 gigahertz, which is in the Bluetooth region. So this is one of the best Bluetooth local oscillator fabricated for graphene transistors. And with the graphene transistor, if you activate the graphene transistors, then you can see you can receive information in the form of a binary signal, which is here is IBM letters, and they are converted into zeros and one, and you can transmit that information. And this is the output signal which is collected here at IF, and this is the at the receiver side. So this is a graphene based radio frequency receiver integrated circuit. And to end my presentation, so this is one of the interesting and one of my favorite example in which researchers from University of California, Santa Barbara, 2 years ago published a paper in which they fabricated on-chip integrated inductors using graphene. So what you are looking at here, this is a coil-based inductor, and it is a thickness from tens of nanometers to thousands of nanometers. So these inductors are compared with the copper inductors, as I just mentioned here. So these are the copper metals, and its thickness is 1 micrometer. So if you compare the inductance value of these graphene inductors with the copper, then you can see this is the dotted red color line where the maximum inductance obtained is 1.2 nanohenry. But for a graphene inductor, you can get about 2 nanohenry value. Okay, so this is a scaling graph where it shows you cannot make any good graphene inductor, copper inductor if you make its thickness below 200 nanometer. Okay, and that's why in the previous paper they used a thickness of 1 micrometer. But with a graphene, you can have a larger and larger inductance with smaller thicknesses, and that is what is called as a contributing to a nanotechnology. Okay. So to summarize, nanoelectronics is a progressive field, especially with RF and bendable electronics, and that's why new lithographic techniques needs to be invented to fabricate novel device components and circuits. Okay. So thank you for your attention, and now you can ask if you have any questions. Madam?
Sir, good morning, sir.
Yes.
Sir, this is Arunagiri. So I have a doubt regarding a molecular addition lithography you are told regarding Cambridge, London.
Which vendor?
Sir, molecular addition lithography.
Right, yes, go ahead.
Sir, is it available in India, or we have to approach them for that technology, sir, for other applications?
So actually this is a technique which you can develop in your own lab anytime.
Oh, okay, sir.
There is no any special tool is available for it, but if it just as you can see it here, you can see the paper and you can develop this technique in your own lab.
Okay, sir. Thank you, sir.
Yeah.
Participants, if you have any queries, you can ask now.
Yes. Hello, sir.
Yeah.
Sir, what about the selection of SRMIST materials?
Selection of?
SRMIST.
I didn't hear you. A little bit louder.
Sir, in molecular addition lithography,
right.
So we are selecting the material, right, sir? So it is different for different metals, or we can choose the same materials for addition.
Yes. So in this one, what it needed is actually you select the materials or the metals as your requirement. So you can select the metals which has a work function smaller like 4 electron volt up to larger work function of platinum which has a 5.5 electron volt. So these are the lower and the upper limits for work function. Okay. Then corresponding to that, you can choose your semiconductor.
Okay.
So as long as these materials are available in your deposition technique, so there is not any restriction of the lithography point of view.
Okay.
Yeah.
And sir, in graphene electronics, we are fabricating graphene transistor for high frequency.
Yeah.
So it is because of the mobility or any other parameters?
Yes, as I just mentioned, the mobility is one of the important parameters. For the transistors.
Okay. Any other materials? So can we use some kind of superconducting materials?
Yes, of course. That can maybe ideal material to use, but operating temperature is the challenge there, because till to date we don't have room temperature superconductor.
Okay. Okay, thank you.
Yeah. So it looks like there are some questions in the chat box. So let me see. Yes, you can put your comments in chat box also.
Sir, you can also share your mail ID, sir.
Yes, I already did it on the first slide itself.
Okay, sir.
Okay. Yes, so the open source software for the fabrication. So actually, I am not sure what this question is from Shweta. So the fabrication software, you mean a design software? So there is a couple of softwares are there. You can easily Google it and they're available for the designing, to make the design. But as far as the RF performance is concerned, there are only one or two softwares, but most of them are actually paid. Yeah, apart from that, there are no any questions in chat box. So if madam are available there.
Okay, sir. There is one question from chat box, sir.
Yes.
Sir, for academic level, what type of projects can we give to students?
Yeah, so actually this simulation software can be actually purchased in our department, and we can make them available to students and make them actually because they are very energetic, the BTech students. And if we just tell them to make one particular design, so they can show us very quickly what kind of cutoff frequencies we will be getting. So these are actually the quick project. As far as the fabrication is concerned, from experimental point of view, they are a little bit tricky, because right now, depending on which place you are, fabrication is challenging. But from simulation, you can always collaborate with people in big institute who has the fabrication certification, and contact them once you make new design. Please contact them, and you can help them, take their help in fabricating the devices.
So that's all.
Yeah.
Thank you, sir, for your wonderful. Now I request Ms. Akshaya to deliver the vote of thanks.
Very good morning. I, on behalf of Head of Department and Department of E&I, SRMIST, I take this moment and extend a very hearty vote of thanks to the speaker, Dr. Abhay Sagit, sir, Associate Professor, SRMIST, for raising your important work and sharing with us your findings and opinions today, sir. Also, we are really enlightened with your knowledge in nanoscale device for RF electronics and fabrication techniques. We are grateful, sir, for explaining on the topic materials and its interfaces, surface and its interfaces in a nano world. I may like to express our sincere thanks for giving an excellent coverage to the lithograph techniques, sir. We're all inspired and benefited by your great talk, sir. Thank you once again, and thank you all.
Thank you.
Participants, your next session will start at 11:15 a.m. Thank you once all.